Okay, in this video we're going to have a quick look at work and simple machines. So let's have a look. Alright, so let's start with work. Work is something a little bit different from what we normally refer to in everyday life. Work in science, so we use the symbol here W, and this is I'm going to write the format you're normally given. So work is equal to force times distance. So we've probably looked at forces already, if you probably watched some of my other videos, and forces are measured in something called newtons. So force is a push or a pull, and it's measured, the size of the force is measured in newtons. Our distance here is just measured in meters, so you're probably familiar with that. So work is when we push an object with a certain force and it moves a certain distance. Now work, the unit, is actually in joules, which you'll notice joules, if hopefully you remember, is the unit for energy. So basically we're saying this is the energy that's needed to push a certain object with a force, with a certain size force, a particular distance. So we might say, it takes 100 joules to push a block with 10 newtons for 10 meters. Right? So work is the amount of energy it takes to push or pull an object with a particular force through a particular distance. Now you can put that into a triangle like this. Right? So it might be handy to learn the triangle. Now in your formula we can see if W is at the start, nothing's on top, so it'll go on the top of the triangle. So it's a little trick I've taught my classes. If you've got a formula like velocity equals distance over time, whatever value's on top will go on the top of the triangle, and if it's a flat formula like this, nothing's on top, then you use the first one. Alright, so anyway, so we can use our triangle to rearrange this formula. So we can go here, for instance, if we want the force, we could say force is equal to, and it's going to be the work divided by distance. And if we want the distance, we could go distance equals work divided by force. Okay, so it's just rearranging this triangle here. Now, just before I move on, just to quickly recap, so work is the amount of energy that's transferred or transformed when we push an object with a particular force through a certain distance. So it's the energy needed to push or pull something with a particular force through a particular distance. Okay, let's have a look at an example. So I'll just... Okay, so a woman pushes a child in a buggy up a ramp as shown below. The woman pushes the buggy up the ramp with a force of 100 newtons. Calculate the work done to push the buggy and the child up the ramp. So we can go work equals a force times distance. So my force, it's told me here, is 100 newtons. And my distance here, well, what's the distance? They've given me 2 here. They've told me the ramp is 1 meter high and it's 6 meters across. How do I know that I've got to use this 6 meters over here rather than 1 meters? Well, the work done, the work that she's going to do is the force she pushes on her little pram with, on the buggy, and it's the distance that she pushes it for. So she's actually pushing it along the ramp. The other reason we know it's the 6 meters is if we're calculating work, the force and distance must be essentially in the same direction. So she's pushing in this direction, so we've got to take the distance that's in that direction, right? The same kind of distance. So this distance over here is really not particularly relevant to us. So it'll be the distance is 6, and so our answer is, there's a space for it over here, 600, and the unit for energy is joules. So it will take her 600 joules to push her buggy up the ramp with a force of 100 newtons. Cool, I hope that was clear. You can always jump back and have another listen. Alright, so what we're going to do now quickly is we're going to look at some examples of what we call simple machines. And the ramp was already one, but let's have a look. So let me zoom in here. Alright, so to start off, guys, simple machines include things like inclined planes, which are basically ramps, levers, pulleys, and gears. These devices can help us to do things by changing the size of the force, the direction of the force, or the distance something moves. Now, simple machines can either be force multipliers. What that means is they increase the force, but they actually reduce the distance that you get out. Or they can be distance multipliers. They increase the distance something moves, but you get less force out of it, so you'll have to put in more force. So let's take a look. So basically what we're saying is here, there's a trade-off. All our machines, with all of these machines, there's a trade-off between the force and the distance. And so you can improve one, but you affect the other one the other way around. So, we can make something put out a bigger force, but it'll put out a shorter distance. Or we can make something put out a greater force, but it'll put out less distance. Alright, let's have a look. So, an inclined plane. Alright, an inclined plane is a type of simple machine, and it includes things like ramps or screws. So a screw here is actually an inclined plane. It's like a ramp that spirals around the screw. So think of like a spiral staircase. It's like a ramp, or if you're in a parking garage, when you go around those corners and you drive up and up and up, it's kind of like a spiral staircase. That's an inclined plane, and it's actually wrapped around the screw here. And what they do is these are force multipliers. So you only need to put in a small force, right, because it increases the force for you. However, the object has to be pushed, or you have to apply the force over a longer distance. So there's always a trade-off here. So this reduces the distance the object actually moves for you in some cases. So think about this in terms of like our screwdriver here. Alright, if it was a nail and we just pushed it in, we would only have to push it this distance here. We only have to push it in that far. But because it's got the spiral, a screwdriver, we've got to turn it, and the distance we cover is all spiraled up like this. And you can imagine if I stretched that line out straight, it would be much longer than this one. So the distance is much longer. We've got to turn it a whole lot more. But the benefit is that we get a lot more force out of it. It pushes in a lot more forcibly, or we can essentially applies more force, but we've got to do it over. So we get more force out of it. It multiplies our force for us, but we have to put in more distance. Same with the ramp here. Let's have a look at the ramp again. So like my example before, if we've got a ramp, I've got two options. I could lift an object straight up here, or I could maybe roll it across the ramp up this way. Now if I lift it straight up, I'll probably need a big force, but I only have to lift it a short distance. So what my ramp does is it means that I put in less force, but I have to push it over a longer distance. Now this basically, what we're saying is it ties in with our formula that we looked at before, our formula for work. Because essentially work was, and sorry, I'm going to pick a different colour so it stands out a bit more. So essentially we said, guys, our work was the amount of energy it took to push something, apply a force through a certain distance. But if work is energy, what do you think about the energy we put into something, into say pushing something up the ramp, is always going to be equal to the energy we get out of it. So if work is force times, sorry, that needs to be a capital F. So if work is force times distance, well, what happens is the work we put in, the energy we put in, we often say if I'm turning a screwdriver or pushing something up a ramp, we're putting that energy in as a force applied through a distance. what a simple machine can do for us is it can change the proportion of the force and the distance. So the energy can't change. It's always going to take, we can't create or destroy energy, but we can kind of manipulate or trade off our force and our distance here. And what that effectively means is, so I'll just rub that out. For a simple machine, whatever work we put in, whatever energy we put in, so work in equals, it says win, equals the work we're going to get out. Now what that means is whatever force times distance we put in, so let's imagine I put in a big force and only push for a really small distance, is going to be equal to the work we get out. But what I might get out of my machine might be a little force times a big distance. So what we're essentially saying here is that, you know, that the total amount of energy has to stay the same. The energy we put into something is going to be the same as the energy we get out. But we could put in a big force through a little distance and get out a little force through a big distance. We can trade them without affecting the total amount of energy. So let's have a look at another couple of examples of machines and how they work, and then we'll do a question that actually involves a calculation. Alright, so just go on to the next page. Alright, so levers. Okay, so a lever. Sometimes we call the force that's applied, that we push onto the lever with, is called the effort. And the weight, or the force pushing back, is called the load. Now the point about which it turns, the point on which it pivots, is called the fulcrum. Sometimes it's also just called a pivot, so either of those are fine. So we put in an effort force here, there's a load force here, so this is us pushing down, this is the weight of the object pushing down, and the fulcrum, so the effort, the load, and the fulcrum. So levers can either be distance multipliers, depending on the position of the fulcrum, or distance multipliers. They can be either. So let's have a look at a couple of examples. Alright, so these are our three types of levers, and you don't have to memorize the types for your test or anything, but let's have a bit of a look. Sorry, just get that into position. Alright, okay, so you can actually, what we're just showing here is you can actually have the load on the other side to the force, or these two here, you can see the force and the load can actually be on the same side. So this is like on a wheelbarrow. The pivot is actually the wheel, the load is in the middle, and we're lifting from the end here. So there are different types of levers. The position of the fulcrum, the pivot, and the load and the force can be slightly different for different levers. And this can also give us a slightly different outcome. So let's have a little bit of a look. I'll just draw one up here. Just give me a bit of space. Alright, bring that down. So if I have a lever that looks something like this, so we'll put the pivot over this end, and let's say we've got a load, so I'll do that a different colour. We've got some sort of, just a block or some sort of object on this end, and I'm going to apply my effort force. I'm going to push on this end. Well, what actually happens in this case is that I'm going to push, and my end of the lever is going to move a whole lot. Or we can even, it's actually also proportionate to, we can look at the distance across, this distance here. Now on the other end, the distance here is a whole lot shorter. I've got less distance, and this end, if I push down on this end, or move it a whole lot, up here it's only going to go up or down a tiny little bit. So what we're saying is on this side we've got a big distance, and on this side we've only got a little distance. So what does that mean? Well, it means on this side my force is going to be quite small, whereas on this side, to compensate, my force is going to have to be the big one because I'm only getting such a small distance out of it. So what we see here is that when we do this, you can use this like a crowbar, like the man's doing here, because it's going to be a force multiplier. It makes our force bigger. So what that means is you can imagine this man, when he levers it, he's going to have to move this all the way down here, and on the other end here, it's only going to move up a tiny little bit. But it's going to move up with a whole lot more force, and so he might actually be able to lift or move the boulder. So we're always trading off here the force and the distance for the force and the distance we get out. Because these two multiplied together, the force times distance here is our energy, our work that we're putting in, and this is going to be the work that we're getting out on the other end. So we'll look at an example in a little bit. We'll cover the rest of the machines, and then we'll look at an example that actually involves a calculation for this. Alright, let's go on to the next bit. Okay, so lastly, pulleys and gears. So we'll look at these separately. So pulleys are force multipliers. So these are also force multipliers. Alright, pulleys mean that you only need a small force. So if I pull this rope, I only have to pull with a small force to raise up a really heavy crate or something. And you see this on cranes all the time. Some people use pulleys to hoist their bike at home, to hang it off the ceiling in the garage to get out of the way. But a pulley, if you pull on the rope here, you only need a small force and you can pick up something really heavy. The trade-off though is that you have to pull the rope much further because it reduces the distance it moves. So if you ever have a go at a pulley like this, what will happen is you'll pull down on the rope here and you'll be able to lift something that's really, really heavy because it's going to increase the force. But you're going to have to pull on the rope, pull lots and lots on rope, pull it through, and the crate's only going to move up a tiny little bit each time. So each time you pull on the rope, the crate's only going to move up a tiny little bit. So what it's doing is, it's increasing your force. You're getting a big enough force to lift this really insanely heavy object, but it's reducing the distance. The crate only moves a tiny little bit. So pulleys, that's an example of a pulley. Alright, and we'll have a look then at gears. So gears are basically like a toothed wheel. And one wheel is what we call the driving, has a force applied to it, is the driving gear. So it's the one we first turn, and the gear that turns as a result is called the driven gear. So if we have a look at some examples here, they can actually be force or distance multipliers. So the first one here, it doesn't actually do either. If I drive this gear here around, like it shows here with the arrow, if I turn it this way, the other one's going to turn in the opposite direction. So you can see as the teeth go through this way and pull it down, this one's going to go through and be pulled down on that side. So turning it this way gives us a turning in the opposite direction in the other thing. So this one is just changing the direction of the force, which could still be very useful. So we could a gear can be used to just change the direction of the force. But if we have two wheels of different sizes, have a look at this wheel here. Because this wheel is bigger, every time I turn it around once, is the smaller wheel going to turn around more than once or less than once? Well, if you count the number of teeth, each time the teeth go through, if 3 teeth or 5 teeth go through on this cog, you'll get 5 go through on this one. So what it means is this bigger wheel, if I turn that around once, the little wheel here is going to turn around more than once. So we're going to get more distance. It's going to turn more quickly, faster, or turn to cover a greater distance. So turning the driving gear here, we get a greater distance or it'll turn faster on the driven gear, but it'll have less force. For this one here, we've got a driving gear that's smaller, so every time I turn this around once, the bigger wheel here is going to turn around less than once. It's not going to go quite all the way around. So you can imagine this, the smaller wheel here, smaller gear, if I turn that around once, the big one's not going to go, it might only go around sort of half a turn. So what's happening here is we're actually getting less distance out, but the bigger wheel, the bigger cog, will turn with more force. Okay, now let's have a look at an example of a problem. So we did this one, the ramp. Oh, let's have a look at a lever problem. There we go, nice and big. Okay, so I've got a lever here, and I've got my pivot, the little triangle thing here. I'm putting in my effort force here, and I've got a load over here, a load force. So I might call this the load. Okay, so I'm going to use this sort of setup here for a couple of questions. So firstly, we could look at if this load is, let's say it's 5 kilograms. It's 5 kg. So if it's 5 kg, what's the force actually pulling down on the side? So it would be 50 newtons. It's going to be 50 newtons. Okay, so on this side it's going to be 50. So we know that our mass times gravity, mass times 10, is going to be our weight force. So we've got 50 newtons pulling down on the side. Now let's pretend that this is, let's make it nice and simple. Let's make this, let's pretend it's really, really big. Let's call this 10 meters. Alright, so we'll make it a nice big, or nice, easy number to deal with. Call that 10 meters, and we'll call this one on this side, let's call that 20 meters. It's about twice as long. Okay, so I could ask you what effort force would I need to pull down on this side with to lift my load? So you might think, well, if it was a perfect seesaw, if this was in the middle, then I'd have to pull down with the same amount, or just a tiny little bit more, but basically the same amount, so I'd have to pull down with 50 newtons to lift up this end. But it's a little bit different here because this pivot isn't in the middle. But we can work it out because we know that the work that I'm going to put in here, alright, the energy I'm going to put in to try and lift it, is also going to be the energy, alright, on the left hand side here, it's going to be the energy I get out, the energy needed to actually do the lifting. So the energy I spend applying a force here is going to come out the other end as energy on that end. And what that means is that on this side, the work that I need to do on the effort side here is a force. Alright, my work here is a force times a distance. I'm just going to get rid of that. And the work that I get out, the energy I get out over this side, is my work equals force times distance. So we'll just make it clear, this is the energy or the work I'm getting out, and this is the work that I'm putting in. Now some of you will already be able to see, we could, so the force here that I'm getting out is my load, so we have to overcome this load force, and the force over here is my effort force. Sorry, it gets a little bit hard to write so small with this, it's not so accurate. Alright, so if the work in is equal to the work out, some of you will be able to see then my load force, just put an L, times distance will be equal to my effort force times distance. Alright, and that's because the force times distance we put in is always going to be equal to the force times distance we put out. we get out. So in this case, all right, the distances are different, so we'll get slightly different forces here too. So let's work it out. So the force, the work we need on this end to lift this is going to be our 50 newtons. It's going to be equal to 50 newtons times the distance here, my 10 meters. So I'm going to need 500 joules of energy to lift my load. Alright, so on this end, it obviously means we're going to have to put in 500 joules of energy. We need to put in as much energy in as we get out. So 500, what that means is 500 joules of energy, 500 joules of energy is going to be equal to my force times my distance, which was 20 meters. So we could rearrange this actually here, and we can rearrange that slightly, and we can go force here, and you can use the triangle if you find that simpler. So remember, a triangle is work in the top equals force times distance. So force is going to be work divided by distance. And in this case, we know the work we're going to have to do. We're going to have to put in 500 joules, because that's what we're getting out on the other side, divided by our distance on this side is 20 meters. So the answer here is we need 25 newtons. So what we're saying here is because we've got twice the distance on this side, we're only going to need half of the force, 25 newtons. On this side, we've only got half the distance, so we're going to need double the force, 50 newtons. So you can see that ratio on this side, we've got a force of 25 newtons, but a distance of 20 meters. The distance is twice as big, but the force is half as much. On this side, the distance is half as much, but the force is twice as big. And that's the kind of the moral to the story, is the force times distance that we're putting in is going to be equal to the force times distance we get out, because that's work, and that's a type of energy. So the energy in is going to be equal to our energy out, and energy can't be created or destroyed, so that's why they're always going to be equal. So I hope that made some sense. Alright, so we're looking at whatever side. Now a little trick to how to tackle this kind of problem. You know, if I've told you that we've got, you know, the 50 kgs, or we'll jump straight to, we said 500 newtons. Sorry, no, it was 5 kg, so it's 50 newtons. 50 newtons, one too many zeros. Alright, so let's say we have 50 newtons of force on this side. Try and make that a proper 5. Alright, 50 newtons of force on this side, and we know the distance. Say, so here we said this was 10 meters. And on this side, okay, I told you we had 20 meters. Okay, well, start with, if you ever get a problem like this, start with working out the work on one side. So here, you know, you've got the force times the distance. Work it out on this side, and then, once you've got the work, you can work out the force on the other side, or use that on the other side. So treat each side, start off with, if you've got a lever, start off with one side, and pick the side where you've got the two values you need to work out whatever you've been asked. And then try and apply, you know, realize that the work, the energy on this side is always going to equal the energy or the work that's done on this side. Cool, so I hope that you found that helpful, and you can always jump back and have another look. But we're probably gonna leave it there. So good luck.